So I welcome all the enrolled candidates in the week 4 for the course Water, Society and Sustainability. This is your Priyaman Srivastav, and we will start from where we left last. So as as we as we discussed in week 3 lecture, that if we can bring some real case studies and try to realize the significance of water budgeting in the real life context. So hence, we will be discussing today the real case of Madurai's rural, peri-urban and urban water supply demand issues and their estimation of water budget, for which we will be taking reference from these two papers. The first paper will be on water management using traditional tank system, a case study of semi-arid region of southern India, and second paper will be revival of traditional cascade tanks for achieving climate resilience in drylands of South India. So these two papers will be in our reference today. I hope that you must have read this paper. However, if not, still we will be going to revise both of these papers. However, before we go into the details of these two papers, one thing which must be catching the attention of all the listeners here is what is tank cascade system. I mean, this is, or what is cascading tanks. So in order to understand what is cascading tanks, here is one chapter which was recently published. Tank cascade system in southern India as a traditional surface water infrastructure, a review. I recommend that you may also refer to this chapter for further details regarding what is tank cascade system and how does it function. But for timing, those who are interested to further understand how the system works, so let us try to have some diagrammatic representation of this tank cascade system. You see here, there is an elevation map of a small tank cascade system network. So this is the upstream part and this is the downstream part. So we can see here that this is the demarcation between above the surface and below the surface. So here we can see what is there above the surface and what is there below the surface. So here are clouds. They are resulting into precipitation or rainfall. And these are the structures, these are the tanks basically. So as you can see here, these are earthen embankments which are constructed across streams. Okay, so if there is a rain occurring in this region, so there must have been some streams which is flowing under gravity, and other embankments were constructed across the streams such that we can harvest that surface runoff or harvest the stream in such a way that surplus water from that stream can be supplied to the tank at the downstream, immediately at the downstream. And this way, these all tanks are connected together, and at the end we can see here that the surplus storage from this last tank is recharging water to the river. So this is how the network of tanks perform and actually manages the surplus supply of one tank into the tank which is immediately situated next to the upstream tank. And this way there is an entire network which manages and controls the rainfall. Furthermore, here is another view of understanding the tank system, which is the plan or top view to understand what are the components of the tanks. So if we see, this is the other embankment which I was talking about in the previous diagram, and this is the surface water storage area where the rainwater is harvested or surface runoff is harvested. You can see here that there is a tree belts at the periphery of the tank. These tree belts allow, first of all, it prevents excess evaporation. I mean, more discussion in this paper. And surplus water is taken from this weir, which is a surplus weir, and here the water which is excess is supplied to the tank at the downstream. While in this earthen embankment, sluices are provided. These sluices allows tank water into the water for specific application. For example, here there is a command area, that means agricultural land. So this tank is actually utilized for irrigating the command area or agricultural land located at the downstream of the other embankment or tank bed. Okay. So this is how the entire components of a tank can be visualized, and we have also seen in the previous picture how the tank cascade network actually operates. So yeah, as we had discussed in the last week, let us start with the first reference paper, which is water management using traditional tank cascade systems, a case study of several regions of southern India. Most arid and several regions of the southern Indian peninsula experience frequent drought. To combat this, historically, many water recharge structures, such as tank cascade systems, have been constructed. So this is the tank cascade system which we just now discussed. However, in recent years, performance of these tanks, especially for irrigation and groundwater recharge, is limited due to impacts of external factors that are not scientifically understood. This study, for the first time, aimed to explore spatio-temporal variation of water mass balance components and their impact on Vandiyur tank cascade system in the city of Madurai, India. So when I say spatio-temporal, it means that we will look into account the performance of tank cascade system at both spatial scales and temporal scale. And when I say it is that we will be studying the water mass balance component, it means it is the hydrological budgeting that we have seen in lecture 2. Study estimated water mass balance components for rural, peri-urban and urban catchments across VTCS. So I hope some of the enrolled candidates who suggested as to how the interventions that we do for water conservation may vary from rural landscape to urban landscape. So this paper is actually taking into account 3 landscapes, which is rural, peri-urban and urban catchments. When I say peri-urban, it is emerging area, emerging region which aims to become an urban area. Right? So it's semi-urban. This can be another synonymous term to peri-urban. It is VTCS. When we say VTCS, it is Vandiyur tank cascade system. Vandiyur is the name of the tank, and the entire cascade of tanks which are attached with the Vandiyur is named as Vandiyur tank cascade system. Catchment specific algorithms and water budget equation were used to estimate the volume of hydrological parameters. I hope as of now we understood what is water budget equation. We have seen that during week 1 and week 2 lecture in detail, and we have also visualized the water budget equation in the form of graphs for the hypothetical village that we took into account during week 3 lectures. Additionally, land use, land cover maps were developed to understand the significance of using a water balance approach in understanding the behavior of hydrological components governing the water budget of a catchment. So this is truly in coherence to what we studied during the last 3 weeks. Results indicated a rapid increase in the urban area, up to 300% in peri-urban and urban regions. Urbanization was considered the primary cause of high catchment runoff. So when I say catchment runoff, it is the surface runoff that we had discussed in the last 3 lectures. So because of the urbanization, the land which is available for infiltration was become unavailable, as the concrete land or the surface was closed due to construction activities, which prevented the surface water groundwater interaction, and as a result of which surface runoff increased, which was identified as 40 to 60% of the rainfall. Due to this, seasonal water availability within each tank across catchment was observed inconsistent, which is ranging between 0 and 15%, wherein summer recorded approximately the least tank storage, that is 0 to 8%. In general, study provided an approach for a practical water-focused application demonstrating how the principles of mass balance can help to foster robust water accounting, monitoring, and management. It further emphasized the use of a water balance approach in identifying vulnerable catchments for appropriate tank rehabilitation-based interventions. So, this is how a real case study is conducted for understanding the significance of reviving the tank cascade system, such that it can allow us to make the best use of these tanks in the regular water applications. And the primary focus of this manuscript mostly remained focused towards identifying the water budget components or water mass balance components for rural area and catchments. So this was the abstract of the research article, Water Management Using Traditional Tank Assist Systems, case study of semi-region of Southern India. So before we go into the details of this paper, let's also see what was the follow-up research to this. Another reference paper that will be focused will be revival of traditional cascade tanks for achieving climate resilience in dry of South India. And this is a follow-up paper because in the previous paper we saw how water mass balance components or hydrological variables were taken into account, such as surface runoff, evaporation, evapotranspiration, rainfall, etc. While in this paper, the focus is mostly towards water supply demand aspects. So let us have a quick review of what this manuscript demonstrates. Traditional tanks in arid regions of India have been working to address water demands for the public for more than 2000 years. So, as we have been repeatedly used the term traditional, which indicates that this tank as a system was originally developed some 1000 years ago, here more precisely 2000 years ago, by our ancestors who remained very vigilant and wise enough to understand the climate and thereby come up with these hydrological structures that allowed conserving the water despite having low rainfall in the regions of South India. However, recent decade is witnessing growing domestic and agricultural water demand, coupled with rising encroachment and ignorance towards tanks, consequently intensifying water shortage issues. While climate change is impacting at alarming rates, local agencies have forgotten these tanks that have aided in sustainable water supply solutions for decades apart from municipal water supply. So here we are trying to project that the tank water supply is assisting in municipal water supply or may assist in municipal water supply if they are rehabilitated. This research for the first time estimates water supply demand for an arid region of South India, Madurai, and lists out benefit if tanks were managed and desilted. So you can see here that the primary focus of this manuscript is towards water supply demand, while the focus of the previous paper was on water balance approach or water budget aspects in the form of how much water is available as storage and how much water is unavailable, and maybe contributing as surface runoff, evaporation, evapotranspiration, etc. Exploratory investigations for documenting seasonal, domestic, and agricultural unmet water demand were conducted, followed by their validation through ground truthing across the study period 2002 and 2019. Results indicated high unmet domestic water demand, estimating 73% for summer season and 33% for winter, and correspondingly high unmet agricultural water demand, estimating 90% during northeast monsoon, which is also called as post-monsoon, and 95% during southwest monsoon, which is also called as monsoon season. And I hope you remember these are the same seasons which we utilized, which we used in our investigation during the first 3-week discussion. Erratic rainfall pattern was identified as a major cause for higher fluctuations in water availability inside tanks ranging 0 to 50%, while lack of ownership resulted in increased siltation load ranging 30 to 70% of tanks volume. So, as we had discussed in our first 3-week lectures, that how siltation could be a cause behind reduction in the storage potential of any structure, such as pond was considered over there. Here, the consideration is towards tanks. So, since these tanks were not managed properly or ownership of the tanks remained one of the issue, as a result of which it was investigated that around 30 to 70% of the tank's volume is actually occupied by silt. Study found that the major portion of the unmet water demand can be accounted for through rehabilitation of the tanks, as under the rehabilitated tank irrigation scenario, the tank storage could attain 200 to 400% more water than the estimated agricultural water demand. So, as we can see here, that if these structures are actually rehabilitated, then they can not only be able to meet the water demand, but we can meet 200 to 400% more than what we estimated the water demand for agriculture. It was concluded that if the cascade tanks were managed appropriately, they could have positive impacts by reducing floods and providing water for drought seasons. So now I hope you are sensitized enough to understand the significance of these traditional structures, which can actually help us to increase the sustainability of water supply systems. And they can also aid in increasing the storage capacity of the existing structures in meeting various water application demands. Right, so starting with our reference paper number 1, where our focus is more on water balance approach, water mass balance components. So the primary objectives of this study are first to estimate water mass balance components for rural, urban, and catchments of the city of Madurai, and second to explore the spatio-temporal variation of water mass balance components and its impact on the available water resources. The broader intent is to quantify the inflow and outflow hydrological components from their respective catchments, having varying developmental settings. So when I say developmental settings, it is rural, peri-urban, and urban. The secondary objectives of this study are to develop our land use, land cover map showing different land classifications, thereby establishing the relation between land use and water demand. To understand the significance of using a water balance approach and understanding the behavior of hydrological components, covering the water budget of the catchment, and to identify the vulnerable catchments which are critical with regard to water availability and determining appropriate solutions to combat scarcity conditions. So this is what the primary and secondary objectives of this manuscript, which is in high coherence to what we studied in the first 3 weeks. I insist that all the enrolled candidates must read this paper and get themselves more clarified about how these methods are being used for finding the various hydrological components for understanding the tank systems. So here is our study site. The Tamil Nadu located in the south of India, and we have Madurai, which is again located in the south of Tamil Nadu. This is the Madurai, and this is the boundary over which we are making our investigation. More specifically, since we said that we are investigating tank systems, so these are the tanks which are in the network. This is tank 1, tank 2, tank 3, tank 4, tank 5, 6, 7, and tank 8. So there are total 8 tanks in this Vandiyur tank system, and there are 3 developmental settings, which is rural, peri-urban, and urban. So in the rural catchments, there are 2 tanks which are connected together. So surplus water from tank 1 is discharged in tank 2. Surplus water from tank 2 is discharged in tank 3. So I described to you how this surplus water is reaching the tank immediately located next to this tank. That is surplus VM. Then again, the surplus water from tank 3 is discharged in tank 4, and then it is entering into urban zone, which is a vibrant urban region of Madurai. And here is the river. This river name is River Madurai. I hope you have noted the name of this river. And that's why we will be studying the 3 developmental status, that is rural, peri-urban, and urban. And there will be these 8 tanks that we will be investigating to find out how the various hydrological components such as rainfall, surface runoff, evaporation, evapotranspiration, groundwater is actually behaving in each of these settings. And if you start traveling from tank 1 to tank 8, you get this elevation profile, which clearly indicates that this network does not require any pump to operate, because the flow of water from tank 1 to tank 8 is occurring through gravity. So there is a gravity, and this is where the wisdom of our ancestors comes in, where they realized how to make the use of natural flow through gravity while establishing tank systems. So we have described in detail the methodology, and these are the same methodology that we studied during week 1, 2 and 3. The rainfall data was acquired from India Meteorological Department and it was analyzed for 2018. Land use and cover maps were generated using Google Earth Pro. The details of each of these methods are provided here. And surface water storage in tanks was estimated by actually conducting investigation inside the tank. For example, to avoid plausible error in estimation the actual storage, a large number of points were recorded from the field using GPL essential tool by traversing in north-south, east-west, northwest, southeast, and northeast-southwest directions inside the tank on a spread boundary. So within each tank, many points were taken using this tool, this geopositioning system tool, which provided the latitude and longitude of each of these points as well as the elevation from the mean sea level, and on the basis of which we identified the actual storage capacity of each of the tanks. More details in this manuscript. Subsequently, we also identified evaporation and evapotranspiration, for which we use these two equations. In general, this equation is providing us the total evaporation, and here we are estimating evaporation from each season. So we assume that the evaporation is coming from tank, because tank is having water capacity, is having volume of water. So the area of tank is multiplied by the rate of evaporation, and whatever is the water available in each of the season is actually multiplied. So percentage water availability against each season is included. And we are also taking into account the number of days in each season. So in this way, we have identified the water availability in each season, and water availability in each season is further summed together from 1 to t, where t is nothing but 4, where time 1 indicates winter, time 2 indicates summer, time 3 indicates southwest monsoon, and time 4 indicates northwest monsoon. So altogether, we get the total volume of evaporation similar is found for is adopted for evapotranspiration. I hope now you understand what are these processes, and for more details, you may read the theories which are provided in introduction and methodology. Here too, we assume that the evapotranspiration is occurring from agricultural land, which is the green cover of the study region. So the area of the green cover is multiplied by the evapotranspiration rates, and since we are actually accounting seasonal evapotranspiration, so we are multiplying it with the number of days in each of the seasons to obtain the total volume of evapotranspiration. Likewise, we used the soil conservation services government technique to find out surface runoff from each of the catchments. So I hope you realize that some of the hydrological components were directly assumed in our week 1, 2 and 3 lecture discussion. But here we are not simply assuming it, but we are actually estimating each of them. So these are some of the techniques that we use to find out surface runoff from each of the tanks. The listeners can further read it and can follow the references which are provided here for more details. And finally, once we are done with finding all the components such as storage, evaporation, evapotranspiration, rainfall, then we utilize all those information to indirectly identify the groundwater flow. And here is the equation that we used, that is groundwater can be estimated using rainfall, which is P minus surface runoff, R minus evaporation minus evapotranspiration minus storage. So this equation provides the value of G, which is groundwater volume. And here each of this hydrological component is expanded. So precipitation is estimated using this equation, runoff is estimated using this equation, evaporation using this equation, evapotranspiration using this equation, and storage using this equation. So we utilize this equation to indirectly arrive at the groundwater availability in each season. So this equation is nothing but water budget equation that we are using, and we saw the application of this equation, a simplified version of this equation in our weekly interaction. So on each of these hydrological components were analyzed. Here we can see that for each season, how much is the actual rainfall and normal rainfall occurring. And more or less we can see here that the primary monsoon season is the northeast monsoon because this is the study region is Tamil Nadu, and we all are aware that in South India, apart from southwest monsoon, they receive additional rainfall from retreating monsoon or northeast monsoon, so which is dominating season in the south. As we can see here that the actual rainfall accounts for 42% during northeast monsoon season and 34% during southwest monsoon season. While when I say normal rainfall, it is the, the volume of rainfall which is received in the last 30 years. So when we compare the actual rainfall, when I say actual rainfall, it is rainfall between 2002 and 2018, it's the study period. While when I say normal rainfall, it is the rainfall for 50 years, that is from 1969 to 2018. So we are comparing the normal rainfall with actual rainfall, and we see that there is some deviations. Here we can see that how between 2002 and 2018 the rainfall is fluctuating. But most specifically the concern is in the last decade when mostly the water remained deficit, the rainfall remained deficit, and we have also estimated the departure of the rainfall, that is deficiency in the rainfall, and it went as high as 45% to nearly more than 8% of the annual rainfall, percentage annual rainfall. And as was the other objective, the secondary objective remained developing land use network maps, and here we have developed the map. So this is the first tank T1, and which is located in the Kulmangalam catchment. So this is the image of 2002, and this is the image of 2018. So we can see here that between these two study period, how the land use network pattern has changed. More build-ups have come up. Similarly, this is the another tank 2, which is located in the Hooghly region named Veerapandi. And this is tank 3, which is located in semi-urban or peri-urban region, which is Tirupallai catchment. And we can see here there is a drastic change in the land use network pattern as the urban catchment has increased between these two study period. Similarly, this is the tank 4, the part of peri-urban named Serivur catchment, and here also we can see that the urbanization trend is very rampant. While now we enter in the urban region, which is the combination of 3 tanks here, tank 5, tank 6 and tank 7, which are respectively Kosakulam, Parshurampatti and Kodikulam catchment. Okay, these 3 tanks are there, and we can see here clearly how the urban area has increased as compared to 2002 and 2018. And this is the last tank, which is again located in the urban region. The name of this tank is Vandiyur tank, and this is the biggest tank among all the tanks which are located. That's why this entire cascade network is named as Vandiyur tank cascade system. And here is the river bed. So here also we can see that since the urban regions were already urbanized, so we found little more increment because the urban region is already saturated, and that's why the scope of further expansion is little limited. But the case of, say, peri-urban region, there is always scope of expansion. Hence, it is rapidly increasing. The urbanized land cover is rapidly increasing between 2002 and 2018. So, if we want to quantify how built up or urbanized land has increased, so here is the classification. In the urban region, we can see that the increment is very significant with respect to 2002, this is called shown in yellow, and in 2018 which is shown in black. While the same for peri-urban is falling urban area, and the increment in the built up land use is very less in rural area. And if we look into account the agricultural land cover, we see that the agricultural land cover mostly remain dominant in rural areas, and it has increased. If we see here, soil, it has decreased but the decrement in the actual land use from version 2, which is dark green, to version 18, which is light green, you can see that the decrement is quite less in rural area, but it is very huge in peri-urban area, and uh, almost similar pattern is followed in urban region. As so, one thing is very common, that how the agricultural land cover has decreased across this 16-year study period, while how the built-up land has increased across each study region, while the increment is very significant in peri-urban and urban region, while not so significant in the rural region. And this is a comparative analysis of percentage change for both agriculture and built-up. So we see here that how the land under agriculture has declined across the study period, and the maximum decrease in the actual land use is recorded below the line, followed by Vandiyur. So this region where the decrement in the decrease in the actual land is high is the peri-urban and urban land use, while it is not so significant in the rural landscape. And the built-up increase remains significant in almost every catchment, but more significant in peri-urban and urban region. Likewise, the study also conducted the hydrological analysis, where we have found the water balance components for each catchment. And here you can see that this is the catchment number C1, this is the Kharagpur bank. And we can see here that against each season, that is winter, summer, southwest monsoon, how each of the variables are behaving. So this is a classic example of how to use water budget equation and determining each of the hydrological components, such as R stands for runoff, G for groundwater, E for evapotranspiration, C for transpiration, S is storage. So we can visualize from here that the northeast monsoon is having more storage, and southwest monsoon is also showing similar storage, while the storage is declining from the monsoonal seasons to non-monsoonal seasons. For example, storage becomes almost zero. In rural landscapes, this is a condition of rural landscape, and similarly for Viramant, which is tank 2, and located in catchment number 2, similar trend was recorded for both of this. Likewise, we have the other two tanks, like this tank 3 and tank 4, which is located in the peri-urban region, and this is how we have obtained the volumes of volume with the TCM. The address unit is 1000 cubic meter. We know how to estimate TCM because we have solved the problem for our hypothetical village and the week 2 and week 3. And likewise, all the hydrological components have been estimated for rural catchment, for urban catchment, that is respectively KPK, which is Kosakulam, Mashuram, and Kodikulam, and Vandiyur tanks. And also we have identified we have conducted the analysis of hydrological components across catchments, which is very much required. So for example, if you want to see how evaporation is behaving across each of these catchments, so we know that we are having 6 catchments, and in each catchment we have tanks. For example, C1 and C2 catchments are rural, C3, C4 are peri-urban, and C5, C6 are urban. And we can see here that during winter the evaporation rates are very high across each catchments, while it is very less in summer because no water is available in the tanks, so that's why the evaporation rates decline, and it is almost nominal in monsoonal seasons as compared to winter. Likewise, we have estimated for evapotranspiration, which is less than the evaporation. So we can see that the rate of evaporation in the study region is supposedly higher. Likewise, we have also estimated groundwater. So we can see here that the groundwater availability is higher in summer. So one reason as why groundwater is high in summer could be asserted to this fact that Mostly during this rainfall season, the rain is occurring and the rainwater is taking certain duration to recharge the aquifers. That's why the groundwater is gradually increasing in winter and during summer. So that's why one of the alternative during winter and summer for getting irrigation water is from groundwater resources. Although, uh, and maybe because since the water requirement should be met from tank as a system, and that's why that is the particular point at from where the water is actually stored and how it is supplied. So that's why that becomes the scope of the present investigation and that we have looked into another reference paper. And you can see here, as compared to other variables, storage is always very less, and that's why that is a concern for the present investigation. While runoff correspondingly is very high. So we see here that the percentage volume of catchment hydrogen components is always having the same scale, that is 0 to 75%. And in general, if we have a glance of the performance of each variables, we see here that the most dominating hydrological component is runoff, while the most recessive hydrological component is storage. So we can arrive here with a primary conclusion that since the surface runoff is very high in the study region, that may be one of the primary causes behind water shortage. And based on this discussion, we arrived at some of the field level interventions to be included in each of the study region. So, for example, if we look into some of the interventions in rural scale, we see here that channel bed modification is listed in both the rural landscape. Desiltation of tanks and wide river is listed. Then reuse of silt obtained during desiltation. So I now hope that you understand that when we say reuse of silt, it is actually being utilized as manure in agricultural use. And similarly, there are so many intervention, field level intervention that has been proposed, and the description of each of the interventions is described in this manuscript. I suggest that you please read this paper and find out the details of each of these interventions and how they will be incorporated in each of the study regions. So we have also showed the priority as which intervention should come first and in which study region. And we have also provided some future directions, and one of the future direction was accounted in this manuscript, where we have actually taken into account the supply demand aspects. So with this, I suggest all the enrolled candidates that you please go and visualize and see how the revival of traditional cascade tanks for achieving climate resilience is conducted for drylands of South India. And it is a very interesting research where the supply and demand aspects has been taken into account. So let's quickly review some of the findings from this manuscript because it is a follow-up of the previous research. We have the same study area. I suggest that you also read the methodology and see how field level interventions and qualitative and quantitative investigations have been conducted to acquire the knowledge. So both primary and secondary data sources have been utilized. Right. So the things which are in addition to the previous research is identifying the domestic, agricultural and unmet water demand. So this is the equation to find out the domestic water demand. So we are taking into account the population in the year 2019, the season, a particular season where we want to find out the water demand, and the number of days corresponding to that season. Then when we add all this water from season 1 to season 4, we get the total domestic water demand. Similarly, we have estimated the agricultural water demand, and we have seen some calculations in the week 3 investigation. So I hope whatever we covered during week 3, the description regarding equations can be found here in this manuscript, and that's why if the week 3 material and this paper can be seen together, if studied together, then more clarification will be achieved. regarding the water supply demand aspects and estimation of basically the water demand. And likewise, we have also estimated the unmet domestic water demand and unmet agricultural water demand using this equation. So, kindly look into the details. However, in general, if I want to describe how unmet domestic water demand for urban region has been estimated, so we took into account the number of days in the urban region for that particular season and how much was the demand actually, how much was the water demand during that particular season and how much is the municipal water supply in that season. So the difference between the two will provide us how much is the unmet domestic water in urban region. Likewise for agriculture, we now know how much is the agricultural water demand corresponding to each season and how much is the water supply available from tanks. So if tank as a system is taken alone as an irrigation source, then how much water is available in each season from tanks to irrigate the agricultural land, and the difference between the two will provide us how much is the unmet domestic water demand for agriculture. And we have followed the similar methodology as discussed in the previous paper to determine the tank storage capacity, and we have provided some of our findings from qualitative investigation as well as quantitative investigation. There are further details into how rainfall is behaving across the state between 2002 and 2018. And this was our estimation for finding the population in 2019 by considering the census data from 1991, 2001 and 2011. And this is our first find regarding water supply demand aspects. So volume has been estimated in 1,000 cubic meters. Now you know that how to calculate this volume in DC. So calculations regarding how to calculate each of them for each season has been shown in week 2 and week 3. I suggest that you follow the YouTube videos of week 2 and week 3 lectures. If I describe this figure, this is the season-wise and catchment-wise volume of water availability. For example, how much is the domestic water demand is shown in here, and how much is the municipal water supply which is supplied in each of the catchments, and how much is the unmet domestic water demand, which is the subtraction between domestic and municipal water supply. So we can see here clearly that in summer the unmet water demand is very huge as compared to monsoon seasons, where the unmet water demand is less, and also we see that there is a sharp variation in the domestic water demand, where the demand is higher in the southwest monsoon and northwest monsoon season, while the demand is also very high during summer, but not enough water is available, and that's why this is creating water shortage issues during non-monsoon seasons, especially in summer, as well as winter is also witnessing water scarcity issues. Similarly, for agriculture, we have identified that the actual water demand is very high in catchment 6. And one interesting fact is that the agricultural practice is not occurring in each season. For example, in each catchment, for example, we have C1 to C6, 6 catchments in there, but we found that agricultural activity remained dominant in catchment 1, catchment 2, which is representing rural landscape, and catchment 6, which is the vibrant urban catchment of Madurai. So only these 3 regions were actually involved in conducting the agricultural croppings, but other catchments discontinued cultivating crops, and the reason which was avoided by farmers is the non-availability of water. So now you can imagine the grave issue which is persisting in the Madurai. Since the water is not available, hence farmers have left their land abandoned. They have abandoned their land and they are now switching for some alternative jobs rather than staying in agricultural profession. And this graphs and the findings is sufficient enough to showcase the issue which is dominating over there due to water scarcity for irrigation purpose. And we have also taken into account the groundwater availability. So we found that in the urban region, which is this, how the depths to extract groundwater is very high. For example, in the vibrant urban region, the depth of extracting groundwater resources is as high as 100 to 300 meters as compared to the belts which are located in the rural region, which is somewhere around 500 meters. So, and across the study period, we see that the depth to extract groundwater is increasing, and now the influence of the unavailability of groundwater at lower depths is uh, increasing, and it is now expanding from urban to peri-urban region, and that's why it is we are suspecting that the similar water crisis issue may reach to rural landscape as well. However, the rural landscape is currently protected, and we are having sufficient wells as well as water available in the wells for having for practicing the agriculture. But as far as the urban region is concerned, the water is scarcely available for irrigation purposes as well as for meeting domestic demand. So we discussed that what will be the scenario if we rehabilitate tanks, and before we go into the rehabilitated scenarios, let's also check the status of the tanks. So here are the 8 tanks that we have seen across 6 catchments, and we found that how much is the silt available in each of the tanks. If you see here in the urban tanks, the silt content is very significant. For example, here we see that this is the Vandiyur tank, and the volume of silt is very huge. It's like more than double of the total storage capacity of the tank. So we also identified that the availability of high quantity of silt in the tank is one of the concern of low storage potential of this tank cascade system. We also found the water availability in the tanks across each of the season, that is winter, summer, southwest monsoon, and northwest monsoon. And we found that the water availability is very less during summer. And in general also the water availability is very less across each of these seasons. For example, the maximum water is available during northeast monsoon. That is to reaching just 50% of the total storage capacity. And remember, when I say this is the percent water availability in the tanks, this is excluding the silt. So you see here that if the storage capacity is 2629 thousand cubic meter of water can be stored in tank 8. So of this tank volume, we are able to have nearly 20% of total volume of water available in the tank during northeast monsoon, which declines to 10% during winter and remains 10% during summer as well. So I hope now you are able to understand that even whatever is the volume available to store the tank, to store the water in the tank, that much volume is also not occupied, and the availability of water is very less as compared to whatever the potential of the current, whatever is the current potential of tank storage. So that's why we came up with the understanding that what if the tanks are rehabilitated. So we now know that the agriculture is being practiced in rural catchment, that is C1, C2, and one of the urban catchments, which is C6. So these are the 3 catchment where agriculture was practiced. However, actual practices discontinued in C3, C4, and C5. But our intention is, what if we revive the tanks and thereby develop scope for having the cropping in these catchments as well. So we here show that how the scope for restoring agriculture practices across C1 to C6 can be done by rehabilitating the tanks. So here we see extra water demand, which can be seen during southwest monsoon and northeast monsoon season. So one thing is very clear, that they are not practicing agriculture during winter and summer season, so they are limited to having 1 or 2 seasons of agriculture, and mostly the crops they are practicing, they are growing is paddy, which requires large quantity of water. More description about how cropping is done in Madurai is described in this passage. So we see here that this is the red here indicates the unmet agriculture water demand, and this dark blue shows the rehabilitated tank storage potential, which is our expectation if the tanks is revived. And we see here that although there is no agriculture water demand during winter and summer, but this is the amount of water that will be available if the tanks are rehabilitated. So corresponding to each catchment, we see here that this much is the quantity of water which is available if tanks are rehabilitated, and then we can utilize this water for agricultural purposes. For more clarification, if we look into the season where actually agriculture is practiced, that is southwest monsoon and northwest monsoon, we see here that, uh, for example, in C1 and C2, this is the water demand. However, if we rehabilitate tanks, the water availability will be, more than 2.5 times of what is the water demand. And that's why we mentioned in the abstract that under rehabilitated tank irrigation scenario, the water availability will be more than 200 to 400% of what is the demand for water for agricultural purpose. Even during even in the vibrant urban region like catchment 6, which is the Vandiyur catchment, we see here that this much is the water demand, while unmet water demand was this much. And if we revive the tank, then we will be able to suffice the agricultural water demand very simply, and we will be able to store some water as well. So not only the tank can be utilized entirely for meeting the water demand of agriculture, but we can also utilize the remaining volume of water for other applications. So with this, I end this presentation, and I hope that you will be going to read these three manuscripts, these three papers. I will be uploading the links of each of these manuscripts in the YouTube link. And if you have any doubts, any further questions, please write to me. Uh, you can write your questions as comments on YouTube, as well as you can also write your queries on NPTEL forum. I hope you enjoyed this 4-week long interaction that we did regarding water budget aspects, and we have today completed one of the real case studies of Madurai. I hope that today's discussion must have given you further sensitization towards how to utilize the knowledge of hydrological budget as well as water budget in the context of both the water resources engineering as well as humanities and social sciences, how both the application of these two domains comes into picture and allow us to have a very comprehensive investigation of identifying the causes behind water scarcity in any settings, whether it is rural or whether it is urban. So once again, thank you, and kindly stay connected and stay tuned for further videos. Thank you.